Welcome friends, in this session of our discussion we will discuss the optimal control using the dynamic programming. So, how we can utilize the dynamic programming to determine the solution of a optimal control problem. Say dynamic programming is an old approach to solve any system using the backward pass. It is principally based on the principle of optimality. What is the principle of optimality? We can define it as an optimal policy that has the property that whatever the previous state and decisions, the remaining decisions must constitute an optimal policy with regard to the state resulting from the previous decision. This is also called the Bellman's principle of optimality. What actually is the meaning of this? Optimal policy has the property that whatever be the previous state and decision, the remaining decisions must constitute an optimal policy. Understand in this way, let we have the optimal trajectory which is starting at xt0 and terminating at x of tf. So, this is my complete trajectory, and let us say jx0 or is the optimal cost to transfer state xt0 to xtf. Let this is representing the optimal cost to transfer the state xt0 to xtf. So, xt0 is my initial state, this is my optimal cost. Let me take a point in between this trajectory. Let us say this is x of Tm and this Tm is less than Tf and greater than T0, and this is I am saying Jxm, this is the optimal cost to transfer state from xtm to x of tf. So, what we are saying, if we have jxtm as the optimal cost to transfer this state xtm to xtf. So, this if xt0 to xtf cost is optimal and this is my optimal trajectory, then the cost to transfer from xtm to xtf will be optimal. So, optimal policy, that the property that whatever be the previous state and decisions, so whatever be my this state, the remaining decisions must constitute an optimal policy. So, what the decisions I have to take from xtm to xtf, this will make my optimal policy. So, this is the principle of optimality. Suppose we say this is xt0 to xtf is my optimal trajectory, and let us say from xtm to xtf we have j dash xtm, the cost to transfer through the dash line is j dash xm. If my j dash xm, so if j dash xm is less than j xm, this means let us consider this is my optimal path from point m to point f. This means if I am taking the optimal cost from xt0 to xtf, that will not be optimal, because then this will be t0 to m and m to f through the dash line. This will be the optimal cost, and this will contradict our initial assumption that xt0 to xtf my optimal cost is x0. So, it contradict. So, this will not be true. So, this means if this is the optimal trajectory, then optimal cost will be jxm to transfer from m to xm only using this dark line. So, this is my principle of optimality on which my dynamic programming approach is based. So, now let us consider a system given as xk plus 1 equal to f of xk uk xk. We are considering a general system with the initial condition as xk equal to 0 as x0, and the cost functional is ji xki equal to j s of kf plus sigma vk uk, and this is my cost functional. Why we are saying the I? So, I is either 0, 1, 2, kf minus 1. This means in my each stage I am writing the value of, so I am starting from x0 to x of kf, and I is varying from 0, let us say 1, 2, 3, 4 and up to kf minus 1. So, I can say this is my j0, j1, j2, j kf minus 1, j of kf. So, what this is representing? j0 is the optimal cost to transfer state from x0 to xf. j1 is the optimal cost to transfer state from, let us say, x1 to xf. j2 transfer the state from x2 to xf. So, these are representing my optimal cost at the different value of this I. As I am saying, my ji is equal to s x of kf plus sigma of this term. So, if I will write j of kf, what is this? This is nothing but my terminal cost, s x of kf. So, this is nothing but my s. So, this will be my last terminal cost, and the whole cost we are considering as ji, means j1, j2 up to, so I is taking the value of, so this I can represent as my end cost, this is my terminal cost as J of Kf. So, if I will write the cost so this will be my optimal cost. So, if I will write the cost at the one point before at Kf minus 1, so my this value will be S x of Kf minus 1 plus, if I is Kf minus 1, so this will be V Kf minus 1 U Kf minus 1 plus V, I have only the one term Kf minus x of Kf minus 1 this is my V, and this cost to be minimum. So, the optimal cost, if I want to write, this is the minimum for the value of, sorry, I have missed the U term here, x of Kf minus 1 U of so, the optimal cost is with U of K minus 1. So, this I am rubbing. I can write this simply as V x of Kf minus 1 U of Kf minus 1 and Kf minus 1. This term plus what is the S Kf minus 1 Kf minus 1? I can write as Kf, so J of Kf. So, with respect to U, if I will find out the minimum cost of this is giving me the minimum cost of J of Kf minus 1. To find this, what we can do, del of J of Kf minus 1 by del U of Kf minus 1. So, this is giving you the minimum cost. Now, if we will go one step more below, J Kf minus 2, this I will write from here. So, this is K is Kf minus 2 to Kf minus 1. So, it will have the two terms plus S x of Kf. So, if I will expand this, this is S x of Kf, my terminal cost, plus if K equal to Kf minus 2. So, this is V x of Kf minus 2 U Kf minus 2 Kf minus 2 plus, so I am expanding this summation term. I have only the two terms Kf minus 2 and Kf minus 1 plus V x of Kf minus 1 U of Kf minus 1 kf minus 1. So, this I can write as V x of kf minus 2 u of kf minus 2 kf minus 2 plus, if I will add s of kf minus 1 v of kf minus 1, this term and this term will constitute nothing but my optimal value, or I can write this as S plus V as x of kf minus 1 u of kf minus 1 and I will get the minimum value of j kf minus 2. The optimal value will be nothing but minimum value with respect to u kf minus 2. This is V x of kf minus 2 u of kf minus 2 plus j kf minus 1 star. So, similarly we can keep on expanding with the different value of the I taken as the kf, starting from the kf minus 1 if I will take. So, I will get this term kf minus 2, I will get this term. So, if I will go for a general value of the k, I equal to k, the optimal value of the jk can be written as minimum with uk, which will be nothing but my v x of k u of k plus. So, if you will see for kf minus 1 it was the kf minus 2 kf minus 1. So, this I can write as simply optimal value at the point j k plus 1. So, general relation I can write in this form. So, this means at any time k using the principle of optimality, my performance index will be jk star xk minimum with respect to uk as v of k uk plus jk plus 1 star x star of k plus 1. So, this means with respect to at the point k, this is x of k, this is the optimal cost to transfer the state from xk to kf, which is equal to minimum of uk vk xk uk or j star k plus 1 x star of k plus 1. In other words, more general form, this relation we are writing as j star x of k minimum of uk v xk uk k, and at this point we already obtain the optimal value of the u. So, g x of k plus 1 we are writing. So, this is at the point k and this is at the point k plus 1, and as we know, we have considered our system as xk plus 1 f of xk uk k. So, in terms of k I can write this minimize uk v xk uk k plus optimal value of, now this is nothing but the function of xk uk k. So, in this solution, if we will start from the kf point, using the backward pass, we can reach up to the j k 0. This means our steps will be find out the jkf at kf point, jx of kf, because this is the terminal cost, I already know this. So, I can find this, then find j kf minus 1, x of kf minus 1. So, I know this optimal, if I know this optimal, I can find this, if I know this, I can find j star kf minus 2, and by this, in this way I can finally find j 0, which is j x of k 0 can be find out. So, using this I can solve this problem utilizing the dynamic programming approach. How actually we will do that, we will see in one example. Let us consider a simple first order system as xk plus 1 equal to 4 of xk minus 6 of uk, where x0 is given as 8. My objective is to determine the optimal control and optimal states for u0 and u1, which is minimizing my performance index as j equal to j0 x minus 2 minus 20 square plus half of sigma k is varying from 0 to 1. So, only the 2 steps we will see how it can be solved. So, for any number of the sequence, then we can develop an algorithm to solve this, plus half of sigma k 0 to 1 2 of x square k plus 4 of u square k. So, we will see how to solve this problem. As we know, what is this value j2 star, this is my j0 is given, my performance index is given as x2 minus 20 square. So, this means at the point x2, this is my optimal cost. So, I can write j2 star x of 2 as x2 minus 20 whole square. So, this is nothing but my whole square. What I will write for my next cost j1 so this is minimum of u1 so what we have the v k k is 1 now. So, v x of 1 u of 1. What is the v x of 1 u of 1 is nothing but my this course. So, my v is half of 2 x square k plus 4 u square k. This is my v. So, I can write this half 2 x square 1 and 4 plus 4 u square 1. This is my v term plus j star plus j star x of 2, and for this j star x of 2 I write x2 minus 20 square, and this is my J1. Minimum value with respect to u1 we have to find. X2 I can write in terms of the x1 and u1 from my plant equation. This is the xk plus 1. So, if I am writing the 2 x2, this is the 4 of x2 minus 6 of u2. So, this means I can write this as minimum u1 half 2 x2 square 1 plus 4 u square 1 plus in place of x2 I will write my plant as 4 x1 minus 6 u1. So, minimum of u1 means this, I have to find the minimum with respect to u1 of this quantity. Let us say my this quantity is h. For minimum of u1, my del h by del u1 will be 0. This means to get this value I have to find this, means del h means this whole quantity in the minimum with respect to u1 I have to find this to be 0. So, if this will be 0, so this will give me the minimum with respect to u1. So, if you will differentiate this, so this will give you, I am directly giving the result, you can try yourself. u1 is 12 of x1 minus 60 by 19. This means we are representing u1 in terms of the x1. Until this state we do not know what is the u1 and what is the x1. This we have to find out. With this value of the u1, my let us say this is u1, this is the optimal value. So, I can find out the optimal value of the J1 x1 using u1 star. Means if I will substitute this value in this relation, this will give me the optimal value of the j1. So, at u point 1, this is my optimal u. So, in the same way we will write for the j0. So, we will write this j0 x0. So, this will be minimum of u0 and this will be half of what the v we have considered here, half of 2 of x square 0 plus this is my 4 u square of 0 plus j1 star x1 and x1 I can write in terms of the x1 in terms of the x0 and u0. So, I can write this as minimum of u0 1 by 2 x square 0 plus 4 u square 0 bracket will not be here. So, 2 x square 0 4 u square 0 plus, like we have seen it here, value of the u1 we are placing in terms of the j1 star. So, my this will be nothing but my f of which is f is a function of x0 and u0. So, my this whole expression which will be my h0 now is a function of x0 and u0. So, my this whole function will comes out to be as a function of my x0 and u0, and this we have to solve for minimum of u for minimum of u0 we can write this as del h0 by del u of 0 equal to 0. So, this we are getting directly, and what is the jf x0 u0? When we are substituting the value of the optimal value of the u1 in the expression of my j1 star which we have derived before. So, my this whole equation will be a equation in terms of the x0 and u0 form. So, I can directly differentiate this with respect to u0 to get the optimal value of the u star 0. This means the optimal value of the so once you will solve this equation, you will get the value as 4.81 using my x0 which is given as 8, because this whole equation is a equation in terms of the u0 and x0. x0 is already given. If I will place the value of the x0 in this relation, I can find the value of the u star 0 as 4.81. So, at this point I know what is my optimal value of the u0. I also know what is my x0 given as 8. If these two values is known to me, I can find out what will be my x1. My x1 is 4 of x0 minus 6 of u0, 4 of x0 minus 6 of u0, and if you will place this value, this is nothing but 3.14 we will get once the x1 is known. So, what the x1 is known, and I have represented my u1 was 12 of x1 minus 60 by 19. So, I already have determined the x1. With this value, my u1 will comes out to be minus 1.175. So, now I know x1 and u1. So, easily I can find out what actually will be my x2, which will be nothing but my 4 of x1 minus 6 of u1, and if this value is known, then my x2 will be 19.61. So, by this example we can see how we can apply the dynamic programming to determine optimal value of the u and optimal value of the state, and with this value at the each step we can also calculate what will be my optimal cost. So, all the parameters can be determined as we go from the backward pass. You can see we have started with the J2 star. So, we will find out the J2 star, J1 star, J0, and once we will reach to the next last step, there x0 is defined. So, we can find out the u0, from u0 to u1, u1 to x1, x1 to again u1, u1 to x2. So, all optimal values of the control, optimal value of the state, and the optimal cost function we can determine using the dynamic programming approach. So, I stop my discussion here. In the next class we will discuss how this dynamic programming approach can be applied to a continuous time system, whether it is possible or not, and if possible then what actually will be our approach. Thank you very much.